Welcome back. Today's class we will be starting with multivariable calculus, and this will be our basis for later on connecting different expressions in thermodynamics, particularly in the derivative forms, which are going to be extremely valuable in our ways to obtain properties. So, one of the important thing which we have done in the last class is to define the potentials. Okay, we have developed the potentials here, and so we knew about, of course, U, but we developed thermodynamic potentials A, H and G, and for A, the Helmholtz free energy, the natural variables, as we know, is T, V and number of moles, and similarly for H and G there are certain natural variables, but these are all energies. Okay, so these are all energy or okay, and energy variables basically, and there is one of the important thing is there is nothing called like energy zero. That's something which we must understand that. So what we typically calculate is if there is a change in the state, then the corresponding the change in the variables we are interested in, such as delta U, delta A, delta H and delta G. So what we will be dealing with in thermodynamics is most of the time is basically change in the such kind of variables. So for example, if you look at a simple example, like say we can talk about state process where we change from state from S1 V1 to S2 V2. Okay, the question would be like what is the change in delta U. Okay. So this could be one of the questions, because for U the natural variables is SV, and assuming that the number of moles remains a constant, and hence with this question is very obvious, and in that case what you are going to do is you are going to do just write down this as an integral of delta U from, let us say, 1 to 2, and you are going to write the thermodynamic expression of du which is Tds minus Pdv. Okay. Now this both we know it depends on the path. So you can come up with a variety of different path in order to achieve this process change from S1 V1 to S2 V2. Okay. Now in order to achieve this, we need to first understand some aspects of calculus, and that is what I am going to do, kind of quick review of that, okay, which is going to be extremely useful in the later part of this lecture. Or in general, the understanding of this multivariate calculus would be quite useful. Okay, so let us suppose that you have a function f is f1 x1, right, and similarly let us say you have this y which is also depends on x and z, and let us say this is a function f2. So therefore f is f1 x f2 x z, and this we may say that this is a function f3 x z. Okay. The question which would be relevant, or rather you would be maybe interested in, is what is the value expression of del f by del x. So what we mean by del f by del x? Okay, so it's not defined until we say what is fixed. Until we specify what is fixed. Okay. So for example, if you say that del f by del x is at a constant y, then essentially I am going to write this as del by del x, and f is f1, so basically f1 x1. Okay, and similarly del f by del x at constant z is going to be del by del x. Okay, in that case I am interested in this basically f here can be also written in terms of x and z, that is f3. So I can write this as f3 x z. Okay. Now you can clearly see that this may mean that in general del f by del x at constant y need not be equal to del f by del x at constant z. So, what is the relation between these two partial derivatives? Okay. So, in order to calculate the relation, we can do a simple exercise. Then we can write df as a function of by taking the partial derivative with respect to x multiplied by x plus del f by del z at x dz. Okay. So, if you consider, in order to find the relation between this, then essentially I can write a differential in this form, because f is a function of x and z. So, I can write in the partial derivatives. Now, if you take this and differentiate with respect to x, keeping y constant, then I can have this expression. So, this will be now in the form of partial derivatives. So, this is now del f by del x z, and this is, if you take a differentiation with respect to x, then this is going to be 1. Okay. So, anyway, this is going to be 1 plus del f by del z x and del z by del x y. Okay. So, now I have this expression, I can further simplify. So, I have now a relation del f by del x y is now equal to del f by del x z plus this relation del f by del z x del z by del x y. So, this is the relation between these two partial derivatives, del f by del x and del f by del x z. So, this was the question which we raised here. So, this is one example or one particular relation which we can use in solving some of the problems. But many times we are interested, as I said, going from one state to another, and this may require some kind of a contour integrals. Okay, that is something which I am also going to now describe that. So, in that case, particularly which is relevant for thermodynamics, would be something like where f is, let us say, a function of many variables. Okay. In that case, I can write df as summation del f by del xi, and here j is not equal to I, where we loop through so that means for all, or rather I should write this as for all xi is xj not equal to I, okay, and this is now dxi. Okay. So, this is the differentiation in this form if you have multivariable. Now, if you integrate this, okay, between two so that we have a two specific state point, then I have this left hand side as x1 xn. This is a kind of a state point which are multiple planes, okay, and then the reference would be f x1 to some other initial point, okay, and this is going to be summation integral of this del f del xi xj equal to I dxi. Okay. Now, the question is, how do you find this path? How do you find the path, or in other words, if I define this path as symbol gamma, so how do you decide the path from going to one point to another? One of the easiest way, if it is a two dimensional or two variables state, then it will be simple, a collection of straight lines. Okay. So, that is something which we can demonstrate for simple problems. So, choosing gamma or path is sometimes tricky business, but the easiest would be to compose this path, or this particular path is composed of straight lines. Or straight segments. Okay. So, let us try to demonstrate this. So, we can consider, let us say, this y and x, and you have a initial point is x0 y0, okay, and finally we would like to go to x1 y1, okay. So, that is kind of a two state point on a y and x Okay. Now, what we are interested is to find out delta f, which is a function of x and y. So, initially this is 1 1, or in the final state is 1 1, and this is initial x 0 y 0, right. Now, this would be, as you can clearly see here, this will be summation integral of that. So, I am going to write this as integral of del f by del x y dx plus del f by del y x dy. So, that would be your summation of integral of this, because there are two variables, hence there will be two terms like this. Okay. Now, here I can choose many paths. So, as I said, the easiest gamma would be composed of straight segments. So, there are two possible ways to do that. One is, of course, I can take it here keeping y 0 constant, and then I take the vertical path, and that would be where I keep your x, keep the x 1 constant. Okay. So, this is something which we are going to say is gamma A. Okay. The other possibility is that we keep this x 0 constant and we do this okay, and then we take this path where we say this is a gamma b. So, we go from here till y 1 and then keep the y 1 constant and go along this path from x 0 to x 1. So, these are two different paths. Okay. So, let me write it out, write this here. Gamma A is x 0 y 0, that is initial point, then it goes to x 1 y 0, then finally to x 1 y 1. Gamma B is x 0 y 0 to x 0 y 1 to x 1 y 1. Okay. So, let us consider the gamma A as our possible path, which we would like to use it in order to obtain delta f, and let us try to develop the expression finally. So, delta f okay, is equal to integral of. So, we will be integrating this thing from, basically there are two segments. If you look at it, there are two segments. This is one segment, this is another segment, right. So, let me put here x 0 y 0 and this is x 1 y 0. So, this I am going to integrate this one as well as this one. So, del f by del x y dx plus del 0 y 0 x 1 y 0 del f by del y x dy. Okay. This is the first part in the segment, and then again I am going to integrate x 1 y 0 to x 1 y 1 del f by del x y dx plus x 1 y 0 x 1 y 1. So, that is this part, and then this is going to be the second part of this expression, del f by del f by del y at constant x and dy. Now, if you look at here carefully, you would be seeing that some terms are going to be 0. Okay. So, let us identify those terms. For example, here the y 0 is constant and you are still integrating that. So, this is not feasible. So, this has to be 0. Similarly, here x 1 is constant here particularly, and this part is have to be 0. Okay. So, now you have two terms in the expression. So, that is your delta f. Okay. And finally, you have this you can ignore this because y is constant. So, you can simply write this term as x 0 x 1 del f by del x y. So, this is for the sake of simplicity, and the other one is going to be this, which is y 0 to y 1 del f by del y x dy. Okay. The for based on basically using gamma A. Okay. Similarly, I can use gamma B. If I use gamma B, I am going to get a different expression. So, without deriving it, I am actually writing it here. Okay. So, these are two different expressions, but since is a thermodynamic, if you apply to the thermodynamic conditions, the changes in the potentials or other variables which are state dependent, the value should be same irrespective of whatever the segments or the paths you have taken. Okay. Now, let us further continue this exercise and try to develop a relation again, something called chain rule and as well as inverse rule. So, this is also relevant in variety of different calculations which we are going to do. So, this is, so let me start with the inverse rule. So, del f by del y z as del f by del y at a constant x can be written as, if f is a function of also z, then I can write it as del f by del z x, del z by del y x. Okay. Now, if f is y, then the left hand side is 1 and this is going to be del y by del z x, del z by del y at x. So, now we can rearrange. So, I can write this as del y by del z x is equal to 1 by del z by del y x, or del z by del y at constant x minus 1. So, this is sometimes called inverse rule, okay, or minus 1 rule here. So, what we are saying is simply that this is nothing but you can just inverse it in this way. Okay. Now, consider z is a function of z x y. Okay. So, this is the inverse rule, and then now I am going to develop a relation for which we call it a minus 1 rule. So, you consider z is equal to z x y, and if I take a differential form of that, I am going to write it like this. So, it is going to be partial derivative of x with keeping y constant plus del z by del y keeping x constant. Okay. Now, if you take a partial derivative, with respect to x at constant z. So, if you do this, the following expression will come. So, we are talking about partial derivative with respect to x keeping z constant. So, essentially this is nothing but 0. This should be del z by del x. So, this must be 1 plus del z by del y keeping x constant, del y by del x z here. Okay. So, you have an expression of 0, this is equal to del z by del x y plus del z by del 1 x. So, now what you can do is you can rearrange. So, if you take this thing on the left hand side, it becomes minus. Okay, and then if you use this inverse one, then one can get this expression as minus 1. If you take this here and then you bring it here, is going to be del x by del z y, that is the inverse of this, multiplied by these terms. So, I am going to rearrange here del y by del x z, that I bring it to the second part, and then del z by del y x. Okay, and this expression is sometimes we call it chain rule also. So, these are very valuable expressions and something which we can now demonstrate in our calculations. Integral of du is equal to S1 V1 S2 V2 TdS. Okay. So, now we know how to deal with this kind of integral. So, we can work on it. So, using the relation of the contour diagram, contour integral, which we wrote here, del f is equal to integral of x0 x1 del f by del x y is equal to y1 dx plus y0 y1 del f by del y x0 dy. So, if we do this exercise, if we make use of this expression which you have used here in here, and then we should obtain del u as S1 S2 T at constant V is equal to V2 V1 V2 P as constant, S is equal to S1 dV. Now, this is something which clearly obtains from the expression of the contour integral. What if we have to find out delta u for a different set of variables? So, S and V are natural variables for u, but what if we are interested, or if we wish, suppose we wish to calculate delta u from state 1 to 2, but these are defined as T1 V1 and this is as T2 V2. So, how do you calculate, because these are not the natural variables corresponding to thermodynamic function u. So, for a closed system, I can write it as du. Now, u is a function of Tv here, which is written, because that is how the system is. So, I can write it again as du by dt, or del u by del t constant V dt plus del u by del V at constant t dV. Okay. So, if you integrate this, you are going to get del u, integral of this as del u by del t V is equal to V2 dt plus integral of V1 V2 del u by del V at t is equal to T1. So, this is for a specific chosen path, for a given chosen path, okay, in the same line as we have done earlier. But the question is now, how do you get this del u by del t and del u by del V? So, to get this differential expressions of u with respect to t and u with respect to del V, we will resort back to the thermodynamic expression of du in differential form, which is T ds minus P dV, and then here we are going to take the differential, partial differential with respect to t with respect to at a constant V, okay, and that is what is here, right. So, del u by del t at constant V is nothing but t del s by del t at constant V, and del u by del V at constant t is going to be t d del s by del V at constant t minus p. Now, this is the two expressions we are going to get. So, one is simply this is, and the other one is this. So, you have delta u as follows: T1, T2, and then I am going to bring in here T del s by del t V dt plus V1 V2 T del s by del V t is equal to T1, and this was V is equal to V2 minus P, add that T is equal to T1, and this is the expression. Okay. Now, this becomes more complicated. Further, the issue is that that we do not usually know S as a function of T and V. Okay. And what we want to do is we want to express this delta u finally in terms of something which we can measure experimentally. Okay. So, what we can measure experimentally? We can measure experimentally PVT relations. Okay. You can change the pressure and observe the change in the volume in terms of the density. You can change the temperature and again find out the changes in the PVT expression. But in addition, we can also calculate Cp, heat capacity at constant pressure, Cv, okay, and we can also obtain something, isothermal compressibility and other terms which I am going to mention it in the later part. So, one of the important thing is that which comes directly from this expression, that we would like to finally convert this all this partial derivative which is not accessible directly into something which we can measure experimentally, and this is where we need to know how to do that, and one of the way is making use of something called Maxwell relation. Okay, so this is where it comes very valuable to make use of this in order to express this derivatives into something which we can measure, and this is something which I am going to describe in the next lecture. I will stop here. So, I will see you in the next lecture.